Okay, so that is the property of DFS. Okay, so it has this, if you mark every node, the starting time and finishing time, recording when it was discovered and when we finished exploring this node, okay, then the start and finishing time of every node have this nesting property. Okay, either those time range, they are alive, one contains each other, or they're completely disjoint. Okay, and another consequence of this in the claim we just saw is that if a node V is kind of reachable from U, namely is in the descendant, you can think of U, then the finish time of V will actually be first before we finish exploring U. Okay. Okay, so let's see that an application of the DFS algorithm. But the first, because DFS is a graph search or graph traversal strategy, so you can just same as BFS, you can use it to answer questions such as asking, is node V reachable from U, right? So you can just start from U to answer this question. You start from U and then you do a DFS. If you ever discover V, then yes, V is reachable, okay? Or you can use this to answer question, is the undirected graph connected? Okay, for that, you pick any nodes to start to run DFS. If you can visit all other nodes, then the graph is connected. If there are certain nodes that is not reachable, then it's not connected, okay? And or how many connect components there are there in the undirected graph, okay? You can also use this to answer questions. So is the input graph a tree? Okay, I'll come back to this when we talk about in 2 weeks from now when we talk about the so-called spanning tree, okay? So this is also using both. This can be answered using both. You can think about this yourself, okay? Using both BFS or DFS. Okay, so what is a tree? A tree is just the, a set of edges connecting all the nodes, yet without any cycle. Okay, all right. So, but using the but can DFS be used to find the shortest path to a source node U? Okay, unfortunately, the answer now is no. Okay, BFS can do it, but not DFS. Okay, but the property of DFS can help us to do other things that the BFS cannot do. Okay, so here's one example. So let's consider the following graph. So this graph, this is basically when you take courses, this is a prerequisite graph. Okay, so every node is a course. Okay, and the edge between them, if you have an edge from U to V, means that U is a prerequisite for course V. Okay, so for example, we have to first take DSC10 before we can take DSC40A. That's why you have an edge from DSC10 to DSC40A. Okay, and you have to take DSC40A before you can take DSC40B. Okay, but between DSC30 and DSC40B, there's no direct prerequisite relation. Okay, all right. Now, so this means the immediate requirement, one course has to be taken before the other, okay? But there's also indirect ones, right? So for example, now, before you can take CSE 151, okay? The prerequisite is DSC 80, okay? However, before you can take a DSC 80, you have to take both DSC 30 and 40B. Okay, in other words, if you haven't taken DSC 30, then you cannot take CSE 151. Okay, so this enforce that the order when you take the classes, even between DSC 30 and CSE 151, even though that you don't have a direct edge between them. Okay, so when you schedule your courses for your undergraduate degree, you want to, because you can only take courses in some sense sequentially, right? So you want to find an ordering, a linear ordering of the courses so that you can take them without violating any prerequisite requirement. Okay, so that means that, so for example, in this case, if I first take mass 18, DSC 10, 20, 30, 40A, 40B, and then DSC 80, then CSE 151, this is okay because I didn't violate any of this prerequisite requirement, okay? But if I first take 10, 18, 20, 40, and 40B, and I take CSE 151, then DSC 30, then DSC 80, then that one is not valid because you are taking CSE 151 before DSC 80. Okay, so our goal in order to have is that we want to find ordering of all this courses, or in general, we want to find ordering of the graph nodes to satisfy all this prerequisite requirement, namely to satisfy all the edges, directed edges here. Okay, now mathematically more precisely, what we are trying to solve is so-called finding a topological order in a directed acyclic graph. Okay, also abbreviated the DAG. So what is a DAG? Well, given a directed graph, a directed cycle is just a directed path with the same starting and ending point. Okay, so from a node to itself. So for example, in this graph here, we have going from C to G to F to, oops. So from C to G, G to F, F to C, this path has start and ends at the same node C. So this is a direct cycle. Okay, you also have another direct cycle, which is going from H to G and G to H. That's another direct cycle. Okay, and you can find other examples as well. Okay, so another example is a bigger one is, for example, going from C to H to G to F to C. That's also a direct cycle. Okay, and a so-called directed acyclic graph, or simply a DAG, is basically a directed graph that does not contain any directed cycle. Okay, so it's a directed graph where there you cannot find any direct cycle. So naturally, this example we have here is not a DAG because it has direct cycles. Okay, this prerequisite course graph that we saw earlier is indeed a DAG because you cannot find any cycles here. So for example, you can go from DSC 10 to 40, 40B, DSC 80, but you cannot come back to DSC 10. There's no path going back here. Okay, so this is a DAG. Okay, so this is a valid DAG. All right, now, given a DAG, given a direct acyclic graph where there's no cycle, okay, a so-called topological sort of this graph is simply an ordering of all the nodes in V such that if you have an edge U and V, okay, then in your ordering, U has to come first, comes earlier than V in this ordering. Okay, so this is a so-called topological sort. Okay, so one way to think about this is that I'm looking at using this example. So I'm looking for a linear ordering of all these nodes. Okay, so that when you draw this edges in this linear ordering, the edge is always going forward. Okay, so as an example, so here is the valid topological sort for this graph. Okay, you can verify. So this is a linear order. And for every edge, say I have an edge going from DSC 10 to DSC 20. So this edge, the starting point always comes earlier in this ordering. Okay, in other words, if I direct this edge, then there's in this linear order, I always direct forward. Okay, so same here, I have an edge from mass 18 to DSC 40. Then this edge here is also going forward. Okay, so this edge is also going forward. So you can verify that all the edges, and from here to here, 40A going to 40B, and 40B going to DSC 80, and then they also have the edge from DSC 82. So this, I now plotted all the edges from this graph. As you can see, they're all going forward. So this is a valid topological sort. Okay, now what is the order which is not valid? Well, if I say that DSC 10, mass 18, DSC 20, DSC 40A, and then CSE. Oops, I forgot to write CSE. This is CSE. CSE 151, DSC30, DSC40B, DSC80. Okay, so if this is my ordering, I only change the position of CSE 151. Okay, now we can see that if you look at all the edges, wait, these are all still fine. Oops. But now this 20 go to this, 48 go to 40B, and 30 goes to 80, and 40B go. However, if you look at this edge, going from 80 to CSE 150, now this edge is going backwards, and this is basically not consistent with the this linear order. Okay, so this is not a topological sort. Okay, so this is not valid, while the first one is. Okay, questions? But note that the topological sort actually in general is not unique. So for example, here, this sequence, this linear order is another topological sort order that's consistent with all the edges. Okay, by consistent, that means that given any edge, given the edge UV, U comes earlier in this ordering than V. Okay, so both of this are valid topological sort. Okay, you can verify yourself. Okay, and the reason why there are multiple existing is because, for example, in this case, I just swapped the order of this two. Intuitively, this two, there's no constraint among the two. So relatively, their order can be swapped. Okay, so that's the intuition. Okay, so what we said is that topological sort of the same DAG are not unique. You can have multiple ones. Okay, all right. So now, why did we define this topological sort only for DAG, namely directed acyclic graph? Okay, and the reason is because that a directed graph can admit a topological sort if and only if this graph is a DAG. Okay, and you may ask why. Well, I mean, consider this example. So let's say this example, we know that it's not a DAG. Okay, and if I try to find an ordering of all the nodes such that, you know, all the edges are always going from a node to someone later than it, okay, then we're going to hit a roadblock. Why? Consider just this three, okay, C, G, and F. Okay, what is the order in what is the order in my topological sort for this three? Okay, so now this edge means that C has to come before G. This edge means that G has to come before F. And then this means that F has to come before C. That's a contradiction, because if C has to come before G, G has to come before F. That means that C has to come before F. But then this edge is opposite. It says that now F has to come before C. So there's no way that I can reconcile with all these three edges. Okay, so if there's a cycle, then we cannot find a topological sort order to satisfy all these edges. Okay, that's why the topological sort is only defined for DAGs. Okay, on the other hand, if you have a DAG, it turns out that as long as you don't have a cycle, then you can always find a topological sort. Okay, and instead of to prove you that is the case, what we're going to do is that we're going to design an algorithm. And we're going to show that we have an algorithm to compute a topological sort for any DAG. Okay, so you give me a DAG, a direct acyclic graph, then we have an algorithm to compute a linear order, an ordering of all the nodes of this graph, a topological sort. Okay, all right. So what is an algorithm? Okay. Now, this is where we're going to leverage the DFS algorithm. Recall that given the input graph, if I perform the full DFS, okay, it doesn't matter which node you start, okay, you perform the full DFS algorithm. And after that, remember that our claim B we introduced earlier says that if node U is reachable from node V is reachable from U, then the finishing time for V will always be earlier than the finishing time for U. That's what it is saying, okay? So if in your graph, you have any way to go from U to V, Okay, so V is reachable from U. Then the DFS would, doesn't matter who you discover first, but the DFS would have to finish exploring V and its descendant before we will finish exploring U. Okay, so the finishing time of V is smaller than U. So we finish exploring V earlier than finish exploring U. Okay, so why is that useful? On the other hand, if you have a path from U to V, namely V is reachable from U, okay, then in the topological sort order, what's the relation between U and V? Well, then so you have a path going from U to V, then we know that along this path, this one has to come before V, and this one has to come before this, and so on. So in other words, in the topological sort order, we have to have U first, and then all these other intermediate nodes, and then V. So V has to come after U in the topological sort order, right? Okay, so this means that in this case, we have to V comes after U in any topological sort. That's a requirement we have. Okay, all right. So what does this imply? Well, I know that if V is reachable from U, okay, then the finishing time of V is smaller than U. And I also know that in my topological sort order, I actually want V to come earlier. So how about we do the following? How about that? What this implies is that nodes with earlier finishing time should actually come later. Oops. Yeah, so nodes with the later finishing time should actually come first in the topological sort order, or alternatively, nodes with earlier finishing time should come later in topological sort, right? Right? So if someone finished earlier, okay, then we actually wanted to come later, because I mean, if V is reachable from U, we want in the topological sort order to come later, okay? So what that suggests is that here's a simple algorithm. Given a DAG, I first perform DFS on this graph, okay? And then I simply output the order in decreasing order of the finishing time. Okay, so this is just so that the nodes with earlier finish time should come later in the order. So I invert the order. I sort them by the opposite order of the finish time. Okay, that's it. Okay, well, what is the time complexity of this algorithm? Well, given the graph performed DFS, we already know this is simply V plus E. Okay, then the next one is that we need to output the order in decreasing order of the finish time. Okay, if you say that now I have to do a sorting of the finish time, or if you have to do sorting, that would take, because now you have V nodes, if you have to do sorting, then that would take a V log V, because I mean you have to perform sorting V numbers. Okay, and but in fact, because the finish time is all just integers, right? I mean, we actually know it's from 1 to, if you have n V nodes, 1 to V, okay? We don't really need to do the sorting, okay? You can just have an array of size V and then fill each of the node into the correct entry in the array, okay? So this step can be done instead in linear time instead of sorting. So we don't need sorting. We do not need sorting. Okay, so because here the finish time is only from 1 to V. So what you could do is that you can simply look at the finish time array. You have an array from 0 to V minus 1, and then for every node you simply fill it. If a node V has finish time So let me actually write it here. So if the finish time of a node is t, you simply fill it in the position t minus 1. That's it. Okay, so this is only linear time, and then you just then read out, you report the nodes in the opposite order in this. You first report here, and then here, here, here. Okay, so that's it. Okay, so this can be done simply in linear time. Okay, so I'm not providing the pseudocode or the Python code here, but you should try to do this yourself to write this simple topological sort algorithm. Okay, all you need to do is do a DFS, and then using this array to report the order of the vertices in a decreasing order of the finish time. That's it. Okay, so the total time complexity as such is V plus E plus linear of a node, which is still order of V plus E. Okay, again, whenever we have the graph and we have the time complexity V plus E, this is basically optimal because this is the size of the graph, both the number of nodes and number of vertices, edges. Okay, so our algorithm is only proportional to the size of the graph, which is necessarily so. I mean, that's the best you can do because you still have to traverse all the nodes and edges before you know whether you missed any edge constraint or not, right? So this is the best, the optimal, the best one can do for this problem. Okay. All right. So this is what we just said. Okay. I just wanted to use this and as a quick example. Okay. So now what do? We first perform. So step 1, we perform DFS. Okay, I can choose any nodes as a starting node. Let me just, for the sake of not that look a bit more interesting, let's actually start to explore using this node. Okay, so now if I start to perform DFS, start from DSC30, so the starting time will be 1, and then I go to this edge and then find 80, so starting time will be 2. And since this is how I discover this node, we put this predecessor in red. Okay, then from 80, I look at the its neighbor, which is CSE 151. So I put the starting time of that to be 3, and this edge is the predecessor of 151 is DSC 80. So I have this. Okay, and then now CSE 151 doesn't have any neighbor, so we're done with exploring this one. So the finishing time is 4. Okay, so then from here we go back to this node, and DSC 80 doesn't have any other neighbor either, so we're done with this one too. So okay, and then we're done with this. We go back to its predecessor, which is the DSC 30. Okay, now DSC 30 doesn't have any other neighbor, so we're done with DSC 30 as well. So we put the finishing time to be 6. Okay, now assume that now our algorithm, we have input all the nodes. Let's say that we scan the remainder, see who we haven't explored yet, and let's assume that this time we found the first one we found, which is unexplored, is DSC 10. So we start to explore this one, which is 6, and next one 7. And from here, we discover DSC 20. So the starting time is 8. Okay, and this is, since we first time discovered this edge is red. And then from here, we discover DSC 30, but that one's already visited. So we don't need to do anything. We come back. And there's no new neighbor of DSC 20. So our finishing time is 9. We're done with this. And there's and then we go back to its predecessor. Its predecessor is DSC 10, and we still have another neighbor of it, which is DSC 48. Okay, so now we discovered a new node, and the starting time is 10. Okay, and from here, we discovered DSC 40B. And this edge is red because we discovered a new node. And then at DSC 40B, we look at its neighbor, we find DSC 80, but DSC 80 is already visited. So that means that we don't do anything, we come back. And there are no more neighbors of DSC 40B. So we now set its finishing time to be 12. Okay, then we go back to its predecessor, and there's no more neighbor of DSC40A. The finishing time is 13. We go back to its predecessor. Now there's no more neighbors of DSC10 to be explored, so we're done with DSC10. So its finishing time is 14. Okay, and then we continue to scan the nodes, and we found that mass 18 we still haven't yet discovered. So we now put its start time, the time we discovered this is 15, and then we discover, we explore its neighbor, DSC40A, but that's already visited. So we backtrack. There's nothing to do here. We're done with exploring this node, and we have that the finishing time is also is 16. Okay, so now that's the first step. And the second step is simply report all nodes in decreasing order of finishing time. Okay, now in the code, what do? You basically, in fact, let me be a bit more precise. Since you only have V nodes, you know the starting time from 1 till at most 2V, okay, because each one can have a start and an ending point at time. So altogether, the discrete time will be 2 times V, okay? So you open an array of size. So this is an array of size 2V, which in this case, 1, 2, 3, 4, so it's 16, okay? Then you simply, for each of the node, you put the corresponding entry to its finishing time, okay? So for example, CSE 151 is put in position, its finishing time is 4, so it's the 4th entry. So here you put CSE 151, okay? And DSC 80 is in the 5th position. Okay, and the last position, 16th, is basically mass 18. Okay, and of course, some of the positions are empty because no one has that as the finishing time. Okay, but now to report it, you simply scan this array backwards. So the first one you report is the one with the largest finishing time, which is mass 18. And the next will be DSC 10, which is in slot here. Okay, the next will be DSC40A. The next will be DSC40B. And then after that, it's a DSC20, DSC30, DSC80, and then last one is CSE 151. That's it. Okay, so this is the opposite order of the finishing time, which you can just put in all this course in the correct array entry, which is the position is their finishing time. And then you just scan the array backwards from the largest index backwards and then report them one by one. And that's it. That's the final output. Okay, so this gives you a valid topological sort order. Okay. All right, questions? Okay, so note that topological sort are not unique for the same DAG. Okay, and in fact, there's also many other ways to compute a topological sort for a given DAG. Okay, with the same time complexity, namely also in time V plus E time. Okay, so many other simple algorithms. We will not describe that here in this class. Okay, all right. To summarize, I mean, what we talk about today is the so-called depth-first search. Is yet another graph search strategy where during the exploration, you always first explore the nodes you just most recently discovered. Okay, those and as a result, because you always explore the nodes which is most recently discovered, so you will finish exploring this newly discovered node first before you finish those nodes which was discovered earlier. Okay, and that leads to this nesting property of the start and the finishing time. Okay, in particular, if a node V is reachable from U, that actually means that the exploration of V will be done first before you finish exploring the node U, which has a path leading to V. Okay, And this nesting property is kind of useful in helping us to, for example, to compute the so-called topological sort of a directed acyclic graph. Okay. All right. And this is what I want to talk about today. And the next class we're going to, so far we have been looking at the graph as an unweighted object. Okay, next time we're going to consider graph where the edges also have weights and talk about the shortest path in that context. Okay, that's all for today.